Okay, Drew, what do we do to find the velocity and acceleration? All right, so we're going to take the derivative. That'll be our velocity. And what will that be, Drew? 3t squared minus 12t plus 9. Okay? And then if we take the second derivative, that'll be our acceleration. And we will get 6t minus 12.
Yes, sir.
Okay, so there's a part of that. That's just said find the velocity and acceleration. There's a part right there. Now B part says find the open t intervals on which the particle is moving to the right. Okay? What does it mean to be moving to the right? Going positive on the x-axis, meaning the speed is not necessarily increasing, but the speed is positive. Okay? So B part really is saying when is the velocity greater than 0? That's really what we're asking. Now understand, the velocity can be positive but the acceleration negative. When you put on your brakes, you're still going forward, but you're slowing down. So that means the velocity is still positive because I'm still moving forward. The acceleration is negative because I'm slowing down.
In cartoons, when the character turns around as they're running and they stop, they're still going that way.
Yeah. Mm-hmm. So let's see. So what do we need to do to find out when the velocity is greater than 0? Set the velocity equal to 0. So I'm going to factor this a little bit as I go. 3t squared minus 4t plus 3 equals 0. T minus 3, t minus 1. So that tells us the velocity is 0 at these two places, at 1 and 3. Okay, so get the picture of what's going on. At 0, I've got a velocity of 9, so I'm moving in the positive direction. And then at 1, I stop. What could I do after I stopped? I could go forwards or backwards. So we still don't know if it's positive or negative yet. What do we need to do now to determine where it's positive and where it's negative? Sign line. So that's what we'll do now. We'll create a sign line for our velocity. Our two factors are t minus 3, t minus 1. I'm going to write 3 up here because it is a factor, even though it's not going to play into it. We've got 0, 1, 3, 5. Where did I get 0 and 5 from? Original problem said between 0 and 5. Do I have to worry about to the left of 0? No. So I just need a number between 0 and 1, like a half. 1/2 minus 3 is negative. 1/2 minus 1 is negative. So that's going to mean it's positive. So from 0 seconds to 1 second, what direction am I moving? To the right, because I've got a positive velocity. All right, what if I put 2 in here? 2 minus 3 is still negative. 2 minus 1 is positive. So it's negative. So tell me what happens when I get at 1 second. What do? I change direction. I turn around and start going the other direction. And I keep going in that negative direction until I get to 3 seconds. Well, what happens at 3? If I put 4 in there, 4 minus 3 is a positive number. 4 minus 1 is a positive. So at 3 seconds, what do? Stop, and I turn back around. Okay? So at 0, I'm moving this way to the right. At 1, I stop and turn around. At 3 seconds, I stop and turn around. Okay? That's what we know so far. So the open intervals on which the particle is moving to the right is?
0 and 1 and 3 and 5.
Yep. So it is moving to the right. The velocity is greater than 0 from 0 to 1 and 3 to 5. Is that complex?
If I looked at it, it would be, but
yeah.
you walked me through it.
Now, find the velocity when the acceleration is 0.
So put in 0 for t. Or we set the acceleration equal to 0.
Set the acceleration equal to 0, okay?
Solve the 2 part 2 and velocity.
Very good. Acceleration to 0. So C part, we're going to set the acceleration. Let's do this right. We're going to set the acceleration equals 0, which is 6t minus 12 equals 0, which is t equals 2. And we want to know the velocity at 2 seconds, right? So we're going to plug the 2 into our velocity function, which was 3t squared minus 12t plus 9. 3 times 2 squared minus 12 times 2 plus 9. That's 12 minus 24 plus 9 is negative 3. So the velocity at 2 is negative 3. What does that mean is happening at 2 seconds? I'm moving which direction? Backwards to a negative direction. Does that agree with what we just said in B part?
Yes.
Yeah, because from 1 to 3 we were moving negative. It's always a good practice to get in of just looking at everything and see, do all of my answers make sense? Some of you ran into that on the LN problem on the FRQ, where you've got to find the range. Well, if I've got a max but no min, then that answer's got to match up. Everything's got to match up there with our answers. Does that help? Okay. Now, we're not going to go through 82 because it's asking the same questions. So it would be the same thing in order to do there. Let's move on over to 84 now. A particle, initially at rest, moves along the x-axis such that its acceleration at t greater than 0 is this. At t equals 0, the position is x equals 3. So before we even read the questions, let's write down what we know. Huh?
No, I read A part, I'm sorry.
Okay. What do we know now?
It was at rest.
It was at...
Velocity was 0.
So the initial velocity is 0. Okay. What else do we know?
Time is 0.
All right. At t equals 0, v is 0. Do we know anything about the position at that time?
X equals 3.
Okay. X equals 3. So we know all of that information. Now the... And we know?
Acceleration at time when t is greater than 0
Is
given by
cosine t. Okay, so we know the acceleration. So now, on to Samuel, find the velocity and position. What do we do? Integrate, okay? So for A part, we've done this problem quite a few times now. We're going to integrate the acceleration. Okay? When we integrate cosine, what do we get? Sine. So we get the sine of t plus a c. Don't forget that.
Yes.
How do we figure out what that c is now?
We can plug
in
stuff
for the t
in.
instead of equal.
Yeah, we can put 0 in for t.
And set it equal to what?
3.
Why 3?
Because it's another number that I see.
Okay.
At
0.
At 0 seconds, it wasn't going.
At 0.
Velocity that
Right.
we just found.
Remember, we just found velocity. At t equals 0, v equals 0.
Oh, so we said equal to 2.
Therefore, the sine of 0 plus c has to equal 0. Okay? So now, what's the sine of 0? 0. Now, do you see what I did? Because that's crucial that you know what we did here, because you're fixing to have to do it again. All right? The integration everybody got. Where did this information come from?
The original problem.
We pulled it out of up here. We need to figure out what C is. Remember, going back to the first day we started integrating, we said to find a particular solution, you need an initial condition. Well, we know at t equals 0, the velocity is 0, so we can use that information. Why was it that we didn't use the 3?
We don't need it.
That's position.
It's at the next time.
This is velocity, is all we've got here. This is velocity. So we can't talk about position. If I say you're going 90 miles an hour, that tells me nothing about where you are in this world. Okay? All it tells me is how fast you're going and that you're in danger. So, we get a velocity is simply sine of t. Okay? Now we need to find the position. To get the position, we're going to call that x of t. We're going to integrate the velocity. And if we integrate sine, we get negative cosine of t plus c. All right, we need to figure out what that c is. What information are we going to use this time?
The 3.
Yeah.
Position.
When t equals 0, x equals 3, so we can say minus cosine of 0 plus c equals 3. Now, cosine at 0 is 1. So we have minus 1 plus c equals 3. So we get c equals 4. So our position function is minus cosine t plus 4. All right? Find the values of t for which the particle is at rest. What does it mean it's at rest? Velocity equals 0.
Acceleration might not be 0.
That's right. The acceleration might or might not, but we know the velocity is 0. So we're going to take the velocity function, the sine function here. Velocity equals 0. So that means the sine of t equals 0. When is the sine 0? At 0. Is it anywhere else? Pi.
2 pi, 3 pi, 4 pi, a bunch of other pi.
We didn't have a... What values for t? Yeah, we didn't have where it just said t greater than 0. So yeah. So can you get an idea of what this particle is doing? Okay. Now remember, this is time. 0 seconds, 3.14 seconds, 6.28 seconds.
It's not going anywhere ever.
All right.
So acceleration is also 0.
What do we know here? Let's just take a minute and look. We know when t is 0, the velocity is 0, and the position is 3. So I'm over here somewhere. Okay? Now, we know that if we were to do a sine line, I bet we'd find out that I'm fixing to have a negative velocity. So I'm going to be going over here for a while. And then the velocity becomes 0 again at 3.14 seconds. And I'm going to turn around, and I'm going to go back over here to 6.28. What would be an example of something that does this?
Breaker.
Okay.
Cosine.
This is the sine or cosine curve, but have you ever seen, a pendulum in a clock? You know, it's just swinging back and forth and back and forth. Or if you've ever seen those little ball games that you sit on your desk, so you pick up one over here and it goes, and goes back and forth. Something like that. It's something that's got harmonic motion to it. If you take something on a string and pull it down, not on a string, on a spring and pull it down, what's going to happen when you let go? Up and down and up and down and up and down. And if there's no friction, it's just going to bounce there forever. Okay? So that's kind of what we've got here, something that's going back and forth, back and forth. Okay, understood there? Deceleration. Ooh, if you haven't done your WebAssign yet, this problem could be invaluable to you, couldn't it, Wes? A car traveling at, we got one more after that. A car traveling at 45 miles per hour is brought to a stop at constant deceleration 132 feet from where the brakes are applied. Now, tell me what we know.
The velocity is 45.
Initial velocity is 45. All right.
And when it comes to
All right. What about position, Miranda?
it's
All right? So you're saying the initial position is 132? Okay. She says the initial position is 132 feet. I'm going to choose to change that. Okay? I'm going to say that the initial position is 0. Because I like working with 0 better than 132. And your answer is, well, how can you just change it?
Oh, this is the one we got wrong because you have to turn the miles and feet, and these numbers are huge, and then I got it wrong.
You do? We didn't, did we? And we got it right? Okay.
Because you're talking in miles, but those are in feet, and I was like, what? 32 feet.
Oh, well, 132 is in feet, but we didn't change that, did we? Did we? And we got it right,
Well,
didn't
if
we?
you change it, you get it wrong.
Okay. Well, we didn't. Yeah.
You don't change it?
Yeah, I don't think so.
Which button is that?
I have no idea. It's one of them on the FR, on the. He said it's the last one on the website. But now, understand what I'm saying here. Let's draw a picture. Here's where the car's going 45 miles an hour. Okay? And this down here is where he stops at. Okay? So the velocity at this place, what's the velocity when he stops? 0. Here the velocity is 45. Okay? Now, we need to know something about the position at both places. We could let this position be 132, in which case this position would be 0, but we could also let this position be 0 and this one's 132. It's easier if you let the initial position be 0. How do I know it's going to be easier if the initial position is 0?
Because your history isn't even allowed.
Yeah.
We
It's
have
one
45, and then we have multiply two things by do something with zeros on both sides.
Do you remember a few days ago we came up with some generic formulas for position, velocity, and acceleration?
Yes.
What's the position?
1/2 G
Or A?
squared plus the velocity T plus initial position.
And now look, what am I going to put in this problem now? 0. If I make the 132 up there, I've got to put 132 in here. And then I'm going to have to do something with that. So let's leave it at 0. I think it'll make it easier for us, okay? So now we can say then that our position is 1/2 A T squared plus 45T. Because plus 0 is no need to write it down. Now we don't know what the acceleration is, do we? We're just told that it's a constant deceleration.
But we know that gravity is 32.
Yeah, but gravity is not what's stopping this car.
Brakes are.
Yeah, because this car is moving in this direction. Gravity is always in play if something's going up and down, but this car is moving horizontally. So gravity is not going to play a part in this here.
So we don't need it for A of T?
So we don't need it for A. A is going to be something else. A is probably something we're going to figure out here in a little bit. Okay? We don't know. It's not gravity, though. Well, what else do we know?
Well, in the next problem it asks how much it's going to reduce.
How far has the car moved? So how far has the car moved? So what are we asking for? Position, velocity, acceleration? Position. So we're looking for an X when its speed has been reduced to 30 miles an hour. So what's that 30? A V. All right? So we know this, don't we? Our velocity is acceleration times time plus 45, right? Velocity is acceleration times time plus 45. Where'd that come from? The derivative of position. 2.5 go away, so I get AT plus 45. So these are the two formulas we've got to work with. We just got to figure out how we can use them, or can we use them for A part. How far has the car moved? So we're looking for a position when its speed has been reduced to 30 miles an hour. Any takers? Where can we put the 30 at? All right, so we can take this bottom equation, and if I have no idea what I'm doing, that's all I'm going to do. So I'm going to put the bottom equation down here, what I know, and let's see what I can do. What do you think I can do from there?
Well, you can try it
Negative 15 equals AT. All right.
Well, you have two variables, so you need another equation.
Need another equation.
So you can go plug that back into.
You can't. You've got two variables right there, so you can't plug negative 15 in for anything. Well, I guess actually you could. You could plug it in for 1/2 AT squared and the x one up there.
But you have to leave a t.
Well, you can find out that t equals.
No.
T equals negative 15 over A, and plug it in up here. Yeah. So let's do that. We could say T is negative 15 over A, and we could plug it in up here, couldn't we?
Can we just plug it into that one right
No, because it'll just go.
It'll just go. If we plug it back into itself, it just makes everything disappear. So now, by doing that, we could say then that now our position function is 1/2 A. Now let's don't do it that way. I'm going to change what we're going to do here, okay? What if we solve this for t instead? Could we do that? T is negative 15. That's what we just did.
You can solve for A.
Yeah, let's solve for A. I think that'll be easier.
So negative 15 over t. So it'll be negative 15 over t squared.
So now we get 1/2 negative 15 over t times t squared plus 45t. Well, that gets us
That cancels.
One of those t's will go away.
negative 15 over 2t plus 45t, right? Right? Have we done anything?
Not really.
Not really? Doesn't look like we have, has it?
We've written a whole lot.
We've written a whole lot. So,
Can we, okay, I had it all written down how I did it, but like, can't we try it for like, okay, like, how far can you can't you see, like, solve it first for like everything you know? Which we try to do and see.
all right, let's go back and chase this rabbit again. Everything we've got written up here is fine. We need to find out what the acceleration is.
Take the derivative of the velocity.
All right, and then we just get A. Wow, that doesn't help us. We need an actual number for acceleration is what we need. If we could get a number for acceleration, everything falls into place.
Acceleration, and it's going 45 miles an hour. So the acceleration is negative something or another, but we can figure that out, but I don't know how.
Okay, let's look at this information here. Let's look at what we know is at the finish line here, okay? We know the velocity is 0. So what if we take this bottom equation right here and set it equal to 0? Now that's similar to what we just did, isn't it? But let's take it and set it equal to 0. And why is that a better thing to do? Well, I'm going to tell you why. Because now, what else do we know at this particular time is true? Not only is the velocity 0, but what else is true?
Time is 0.
The position is 132. Okay, so look at what we're going to do. We're going to set this equation equal to 0, and at the same moment in time, we can set our position equation equal to 132. 45t. Now, why is that beneficial? Can we take the top equation now and solve it for A? And if we do that, we could plug it into the bottom equation. And then we just have t's and numbers. So go find it. Go figure out what that is. Take this top equation and solve it for A. And then plug it into the second equation and see what happens. Mm-hmm. Where did my other 45 go? This is 45. This is half of 45, right? So if I take 45 and subtract half of 45, I still got half of 45. Change it. All right, another way to think of this, if I change that into 90 over 2, now I can subtract these, can I? 90 over 2 minus 45 over 2 gives me 45 over 2. Or pick up your calculating device and write down 45 minus 45 divided by 2, and you'll get 45 divided by 2.
Okay, so now we know what t equals.
So we know what t equals. T equals that when?
When the position is 132.
Yeah, when the car stops down here, it takes however long that is. How long is that?
264 over 45 seconds.
Which is what? Round it 3 or 4 decimal places for me,
I
somebody.
got 88.15.
No, can't be right.
88 over 15.
Can't be right.
Like as a fraction?
Yeah, that's not 88 seconds. Oh, 88 over 15. That could be, yes.
Yeah, and then
No,
5.867.
5.867. So it takes almost 6 seconds to stop. Okay? Good. Now, but that has absolutely nothing to do with...
But it does give us a number to plug back in.
But now that we've got our t, can't we figure out what acceleration is? Okay. So acceleration is negative 45 divided by 5.867, which is 1, 2, 3. Negative 45 divided by 5.867.
Negative 7.67.
Okay, so that is your deceleration. And remember, the problem said it was constant, right? So that's the deceleration all the time. Well, how does that help us? Now we can plug that in wherever we've got A's at up here, can't we? Right here and right here. So let's go back and reevaluate our formulas here. Our position formula is now 1/2 negative 7.67 t squared plus 45t. Our velocity formula is negative 7.67 t plus 45. Yeah. And so far we've done none of the problem.
Good.
Great. But A part says, how far has the car moved when the velocity has been reduced to 30?
So it said the velocity
Equal to 30. All right. So if we do that, we get 30 equals negative 7.67t plus 45. Negative 15 equals negative 7.67t. So t equals almost 2, 1 point something. 1.956 t's. Is that our answer?
No, we have to plug that back into the position.
Because it said how far had it moved. So we need to know our position at 1.956. So the position at 1.956 and you have calculating devices, you can figure out what that is. $74 point something? I think that sounds familiar. 73.35. Okay?
This is the one that's
This is the last one on WebAssign. This is the exact problem, I think.
It is. Numbers and everything.
Yeah. Now, B part. What are you going to do for B part?
Well, now that it's speeds introduced, it changes the velocity.
Yeah, you said the V1 equals 15.
Yeah. You do the same thing you did in A part, except instead of this 30, it's 15, and you work through and you get a different time, so you get a different position down here. That's complicated, isn't it?
That was awful.
It was. If you were taking physics, you'd have some other formulas that you could have used to use that, but I think you do. There are some other formulas that you could use, but anyway, since we aren't taking physics, we don't know those. All right, I'm going to leave B part for you to peruse on your own. Let's look at one more problem here, because I think it would be of use to us. Assume that a fully loaded plane starting from rest has a constant acceleration while moving down a runway. The plane requires 0.7 mile of runway and a speed of 160 miles per hour in order to lift off. What's the plane's acceleration? So acceleration is what we're looking to find. Tell me what we know.
Well, when it's 0.7 miles,
Mm-hmm.
well, at the very beginning is above 0.
Okay. Yes. So that is when t equals 0, v equals 0. Do we know the position at that point in time too? 0. How can we justify saying that it's 0?
Because when the position is 0.7, the velocity is 160.
Yeah. When s is 0.7, then the velocity is 160. Okay? And s, I used x of t in the last one. I'm using s here. No, I don't know why. That's just what I wrote down this time. They use them interchangeably there. So that's what we know. When t equals 0, v is 0, and s is 0. So now let's think about that for a second. Here's our formula, right? S of t equals 1/2 acceleration t squared plus v sub 0 t plus s sub 0. What can we do with that now?
Can we use gravity this time because it's going up and down?
All right, but the plane's getting ready to take off. Is it going, how is it going to do that? It's going to be going down the runway. So he's not going, gravity could go into effect if it was a helicopter taking off straight up. But since he's going down the runway, we don't have that to deal with there. But what can you tell me about that formula that I just wrote up there? This is 0. This is 0. What else do we know? V is 0, isn't it?
V 0 equals 0.
All right. So then our position is 1/2 at squared. That's it. If that's our position, what's our velocity? At. Okay. So now what do we need to do? Well,
We can put in our first thing.
meaning
Oh.
We can find A.
we can find A. How can we find A?
Well, we know when t is 0, v is 0.
Yeah,
So we plug that into the bottom one.
but that means A could be anything.
Well, let's do the other one. No, wait.
And that means A could be anything. You're going to do the same thing we did on the other problem. We'll look back at it and see.
Say Vt equals 0 and, oh no. Say
Drew said we could say 160 equals AT squared, right?
Yeah.
Because I say, no, we can't say that.
No, that's AT.
We could say this, couldn't we? 0.7 equals AT squared, couldn't we?
Yeah, but that doesn't help because we don't.
But that doesn't help.
Well, we could solve for t.
Well, we can make
Couldn't we say this? Because at this particular time, now we don't know what time it is, but at this particular time, when he gets to the end of the runway, his speed's got to be 160, so that's got to be equal to AT, and he's traveled 7/10 of a mile, so 0.7 has to equal 1/2 AT squared. So now if you take this bottom equation again, solve it for A or T, whichever one you like, plug it in up here, you'll have one variable, you can do a little razzle-dazzle, you can get the answer out. Which one do you want to solve for, A or T? A. So A is 160 over T. So we've got 0.7 equals 1/2 160 over T times T squared, which that becomes 0.7 equals 80 T. Are we comfortable with that? So 0.7 divided by 80 equals T. Which is a really small number. 0.00875. What have we done wrong?
That's just the time.
The plane accelerates very quickly, Mr. Ely.
You still have to plug it in to find A.
Okay. So our A is 160 over 0.00875. How many of you have ever been on a plane? Do you think you traveled the first 3/4 of a mile down the runway in less than 100th of a second?
No.
I hope you didn't.
We just give up on this and
So what did we miss anything up here?
fast plane.
I don't think we missed anything. What do we get for an acceleration here? 160 divided by 0.00875. I'm really interested to see.
18,285 miles an hour.
Miles per hour.
Warp speed on the bridge.
Okay. We didn't do anything wrong. The problem is a little bit misleading. It says it has constant acceleration. Does the airplane really have constant acceleration?
No.
Because when he's sitting there, it's not like in the movies when he pushes the throttle, it just goes.
No, they put
When
the
he-
throttle on, it goes.
He's starting to move just ever so slowly. So the acceleration isn't constant. If he could accelerate at 18,285 miles per hour,
We would all die.
then he could lift off in 7/10 of a mile, and he would be going 160 miles an hour at that point in time. I don't think that's a really
Our brains
likely
would turn
story.
to jelly.
It would be, yes, it would be ugly there, I do believe. Okay, so that is all of those notes there. Now, I hope that has helped you to understand position, velocity, and acceleration better. So what I'm going to do is I'm going to stop lecturing for the day. You have H27, you have H28, you have H29, you have FRQs, you have WebAssign. That should be enough for somebody to have something to work on there, I would think, with those things.